Let us continue with the revision questions. Question number 1. In an experiment to determine the heat of combustion of compound N, for 4 students of a secondary school in Matungu sub-county used heat from the burning compound N to heat 100 cubic centimeters of water in a beaker. They obtained the following results. The volume of water heated is 100 cubic centimeters, initial temperature 17 degrees Celsius, final temperature 23 degrees Celsius, initial mass of the burner plus compound N is 10.5 grams, and final mass of the burner plus compound N is 10.2 grams. Part A of the question: determine the mass of compound N burned. Now, the mass of the compound N burned will be from initial mass of burner plus compound N and the final mass of burner plus compound N. So if we take this to be Roman 1 and this one to be Roman 2, okay, then to get the answer, we'll say Roman 1 will less Roman 2. That is, initial mass of the burner plus compound N will less final mass of burner plus compound N, which is going to be 10.5 will less 10.2. This is going to give us 0.3 grams. Okay? Yes. Now we move to the next. Temperature will less the initial temperature. So the final temperature is capital letter T2 and the initial temperature is capital letter T1. Okay? So you say what? Delta T, that is temperature change, is equal to temperature 2 will less temperature 1, which is going to be 43.0 will less 17 will less 17.0. So this one you get, you subtract from what do you get? 26.0. So the answer is 26.0 degrees Celsius or Kelvin, because that is a change, a temperature change. So it's either in degrees Celsius or in Kelvin. We move to C. Determine the amount of heat produced by the compound. Okay? Specific heat capacity is equal to 4.2 kilojoules per gram, kilojoules per gram per Kelvin. Determine, density of water is 1 gram per cubic centimeter. So here, heat change is given by delta H. Delta H is equal to MC delta T, whereby M is the mass of water, and our water is 100 cubic centimeters. Now that the density is 1 gram, this 100 cubic centimeters is the same as 100 grams. So here, because our value is in kilojoules, then we put our mass to be in kilograms. So this one will be 100 divided by 1,000. 100 grams divided by 1,000 grams per kilogram. You multiply by specific heat capacity, which is 4.2. And we multiply by delta T, which is our answer up here. So that is the answer for B. That is times 26. What do you get as our heat change? 10.92. Yes. That is 100 times 4.2 times 26 you divide by 1,000. You get 10.92. So this is 10.92 kilojoules. You leave your answer like that. Then lastly, part D, calculate the molar heat of combustion of the compound. And then the mass of our substance is 0.3 grams. So we ask ourselves, if 0.3 grams is giving us 10.92 kilojoules, what about 1 mole of that substance, which is 126 grams? So you just come directly and say, if 0.3 grams is giving us 10.92 kilojoules of it. What about the molar mass, which is 126 grams? Will give us how many kilojoules? So this one is going to be 126. We do cross multiplication times 10.92, and then you divide by 0.3. Okay? What do you get? What do you get?
We get 4,500 and 86.4.
4,586.4
Yes.
kilojoules per mole. Now, when it comes to molar heat change, we must indicate whether the reaction is endothermic or exothermic. So, like for our case, this reaction is exothermic. How do we know that it is exothermic? It is because the final temperature is higher than the initial temperature. Temperature 2, which is 43, is higher than the initial temperature, which is 17.0. So you put a negative behind that to show that this reaction is exothermic. So this is the value, and don't forget this. Don't forget this one, is very important. Negative 4,586.4 kilojoules per mole. 2. Below are heats of combustion of carbon, hydrogen gas, and ether. So this is the enthalpy of combustion of carbon, which is 399 kilojoules per mole. Enthalpy of combustion of hydrogen, 266 kilojoules per mole, and enthalpy of combustion of ethanol is equal to 1,368 kilojoules per mole. By linking the heat of formation of ethanol, that is C2H5OH, to heats of combustion of its components and itself in an energy cycle, calculate the heat of formation of ethanol. So before we go to heat of formation of ethanol, we need to understand that this question is coming from the Hess's law. The Hess's law. What does this law state? According to Hess's law, the energy change for converting reactants into products is the same, regardless of the route by which the change has taken place. So we write that as the energy change for converting reactants to products is the same regardless of the route taken. Are you together? That is the Hess's law. So this question is actually an application of the Hess's law. Now, what do we want to form? We want to form ethanol. What's the formula of ethanol? This is the formula of ethanol. So we start by writing the formula of ethanol, which is C2H5OH. This is a liquid. Now, we are forming ethanol. We are starting from the product, we are moving back. Which are the constituent elements in ethanol? We have carbon. How many atoms of carbon? There are 2. So we write here 2 carbon, which is a solid, plus how many hydrogens? 5 plus 1? 6. So here it is plus 3 hydrogen, which is a gas. Okay, 3 hydrogen, that is 3 times 2 is equal to 6, which is the same as 5 plus 1, which is equal to 6. Plus now, oxygen. Oxygen is a gas, like this. How many atoms of oxygen do we see there? It's only 1. So here we are adding a half a molecule of oxygen. So that is the equation for formation of ethanol directly from the constituent elements. Now, when we burn carbon, what do we produce? We produce carbon oxide gas. Okay? How many atoms of carbon do we burn? There are 2. So you write here 2 to balance for carbon. When you are balancing for carbon, we are affecting oxygen. So how many oxygen atoms how many oxygen atoms have we produced here? 2 times 2? 4. So it means we added oxygen gas. Now these atoms are 4, 2 times 2 is 4. So it means we added 2 molecules of oxygen gas. Okay? Now, when you burn hydrogen, combustion of hydrogen, what do we produce? We produce steam or water. So this is steam being produced. How many molecules of hydrogen did we burn? There are 3. So the product here should also be 3. So when you write 3 here, it does not only affect hydrogen, but it also affects oxygen. So for oxygen, we'll say plus oxygen, like that. How many oxygen atoms? 3 times 1? 3. So here, the oxygen which is added is 3 out of 2. 3 over 2 oxygen, like that. So it is plus 3 over 2 oxygen, like that. Then you get water. Are we together? Now, when we burn ethanol, what do we produce? We produce carbon dioxide and water. So you put a plus in between there. Are you seeing that? So this is an energy cycle diagram. How many oxygen atoms are from the combustion of ethanol? 2 times 2? 4. Plus 3 times 1? 3. So 3 plus 4? 7. So here we are adding oxygen, which is a gas. So this is 7 over 2 molecules of oxygen. That is plus 7 over 2 molecules of oxygen. Are we together? So you have balanced the equation. Let us assume that this is A. Enthalpy of formation of ethanol from the constituent elements is A. While the enthalpy of combustion of carbon is B. The enthalpy of combustion of hydrogen is C. And the enthalpy of combustion of ethanol is D. Are we together?
Yes.
Now let's go back here. Enthalpy of combustion of carbon is what there? It is B. So we call this one B. Are you seeing that?
Yes.
We call it B. Enthalpy of combustion of hydrogen is C. So we call this one C. Very good. Enthalpy of combustion of ethanol is what there? D. Are we together?
Yes.
Very good. So according to Hess's law, we'll say A is equals to, we use now the vectors. We use vectors. To move from here up to here, if this road has been blocked, how will you reach here? Assuming that you have blocked this road, how will you reach here? We use the alternative route, which is what? Going to be, how many B's are here? This is B, isn't it? How many B's are there? 2. So it will be 2B plus, how many C's? Plus 3C, okay? And then, we subtract what? We subtract the D. Why are we subtracting? Because we are going against the R. So it is minus D. So A, to go to A, when A has been blocked, okay, that's the enthalpy of formation of ethanol from the constituent elements. You can use the alternative route if that other route has been blocked. It's not easy to know the enthalpy of formation of a compound from the constituent elements, but you know the enthalpies of combustion. So it will be what? It will be 2 times B. What is B here? 399. So it will be 2 times 399. We add 3C. What is 3C? What is C? 266. So 3 times 366.
266.
It is 266, sorry. So 3 times 266. Okay. Now what we get from this, we less D. What is D? That is 68. This is supposed to be negative. The value is negative here. So the value is negative there. What about these other ones? They are also negative. It's like the writings were not very clear. All these are negative, like this. So these values are negative. enthalpies of combustion. So here will be times negative that one, times negative this one, and then this one is minus negative 1368. Now let us work it out. 399 times 2 is equal to, just press 399 times 2. 399 times 2.
Negative 77.
Negative 798.
Yes.
Negative 798. Okay. 266 times 3. Yes?
Negative 798.
Negative 798. Very good. Plus 1368. Minus becomes plus. What do you get? What do you get? What do you get?
0 plus
Yes?
1368.
1368. Having done our calculation, we have got negative 228 kilojoules per mole. Thank you. And 3. Use the bond energies given in the table to calculate the enthalpy change for the reaction. And this is the reaction that you have been given. Now, to calculate the enthalpy change for this reaction, we need to show all the bonds which are present. So how do we show the bonds which are present? We draw open structural formula. Okay? So this one is supposed to be C2H6. That's C2H8. This is C2H6. And then this one is C2H5Br. Now we draw the open structure. 2 carbon atoms. 1, 2. And then 6 hydrogen. So like this. This is hydrogen, 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 hydrogen. Okay? Now, plus bromine. So bromine we write Br, Br. Okay? Now, what do we form? We form 2 carbon, that is 1, 2, and then hydrogen, that is 1, 2, 3, and then 4, 5, and then Br. Plus now HBr, that is plus HBr. The open structure for these reactions. Are we together? This is the open structure. We have shown all the bonds which are present. Now, we are going to show the bonds of the reactants and the bonds of the products and the bond energies. Now, let's start with the first one. So, these are the reactants. These are the reactants. What is on the left-hand side of the arrow? So on the left-hand side of the arrow, we have carbon-hydrogen bonds. How many carbon-hydrogen bonds can you see? 1, 2, 3, 4, 5, 6. So these are 6 carbon-hydrogen bonds times the bond energy of carbon-hydrogen, which is times 413. You get the answer. The next one is carbon-carbon bond. So we have carbon-carbon bonds. How many carbon-carbon? Only 1. Times the bond energy of carbon-carbon bond, which is 343. This one is going to give us 343. Okay. Then we have another one, which is bromine bond. This bond here. How many are they? Only 1. Times the bond energy of bromine bond, which is 193. So you get 193 here. What do you get here? 6 times 413?
2478.
2478. Good. Now we go to the product side. We see all the bond energies of the reactants. So these are the products, sorry. The bond energies of the products. Okay, the first bond, carbon, hydrogen. Carbon, hydrogen are how many? 1, 2, 3, 4, 5. So these are 5. times the bond energy of carbon hydrogen bond, which is 413 times 413. What do you get?
2065.
2065 kilojoules. The next bond is carbon-carbon. How many carbon-carbon bonds can we see here? Only one. Times the bond energy of carbon-carbon bond, which is 343. What do you get? It remains the same, 343. Very good. Lastly, we have, sorry, not lastly, this is another bond, carbon-bromine. Carbon-bromine bond. This one here. How many are there? One. Carbon-bromine bond, what is the bond energy? 280. What's the total? 280. And lastly, hydrogen-bromine bond. Hydrogen-bromine covalent bond. How many are there? One. Bond energy of hydrogen-bromine bond? 365. What do you get? 365. Now, let us sum. What is the total of the bond energies on the reactant side?
3040.
This is 3014.
Yes.
Okay. What about the bond energies, the total of the bond energies on the products side?
3053.
It's 3053.
Yes.
Very good. Good. Now, how do we get the enthalpy for the reaction? So you'll come here and say delta H for the reaction is equals to enthalpy, okay, is equals to what? Enthalpy of reactants with less enthalpy, with less enthalpy of the products. So the reactants are on this side of the arrow. So that is 3014 minus 3053. 3014 less 3043. 3053, sorry. What do you get? Negative 39.
Yes.
Kilojoules per mole. Alternatively, we can do it in an alternative way. We just look at these compounds or these molecules keenly on the reactant and the product side, and we just identify the side which has undergone a change. So here we have carbon-hydrogen bond. Here we have carbon-hydrogen bond. Is there any change? No change. Are we together? No change. So we leave that. Carbon-hydrogen, carbon-hydrogen. No change. So we leave it again. Carbon-hydrogen, carbon-hydrogen. No change. So we leave it again. Carbon-carbon, carbon-carbon. So we leave that one again. Carbon-hydrogen, carbon-hydrogen. There still is no change. Are we together? Carbon-hydrogen, carbon-bromine. There is a change. Yes. There is a change. So there is a change here and here. That is what. Here we have bromine, bromine, and here we have hydrogen, bromine. Are they the same? No, there is still a change. So this is another side whereby there is a change in the reaction. So we'll come here and then we say which reactants have undergone a change and which products have undergone a change. So we only deal with those sides or the bonds which have undergone a change. So carbon hydrogen, how many carbon hydrogens have undergone a change? Only one. So we'll come here and say carbon hydrogen is equals to 1 bond times the bond energy of carbon hydrogen, which is 413. The answer is 413. Very good. We move to the next one. Bromine, bromine bond. So here we have bromine, bromine bond, which is 1 times the bond energy of bromine, bromine, which is 193 times 193, which is going to give us 193. So we are done with the reactants. Carbon, hydrogen, and bromine, bromine, bromine. We go to the products. Which one has been affected? carbon bromine bond has been formed. So you come here and say carbon bromine. How many bonds? One covalent bond times the bond energy of carbon bromine, which is 280. So you multiply by 280. What do you get? 280. Very good. And lastly, hydrogen bromine covalent bond, which is still 1 times the bond energy of hydrogen bromine, which is 365. You get 365. You get 365. Let us sum up and see what is happening. 413 plus 193.
606.
606.
Yes.
Very good. 606. Very good. 280 plus 365.
645.
600. Very good. So this one is 645. Then we use our formula. Enthalpy of reaction is equals to enthalpy of reactants less enthalpy of the products. Okay? Enthalpy of the reactants is 606. Less enthalpy of the products, which is 645. 606 minus 645, what do you get?
Negative 39.
You get?
Negative 39.
We get negative 39 kilojoules per mole. I hope you have noted that the two calculations are the same.